He was fascinated by the topic and decided to um, wanted to contribute to the global search for it. And fortunately, that passion has stayed with him throughout the academic journey and guiding to now moving to Berkeley to continue the research on dark matter. And he's been living in Berkeley for 4 years now, loves it. It's a great city, which I agree with. When he's not thinking about dark matter, he likes to go on long running adventures to the mountains. He started running 10K distances a few years ago, and nowadays runs 100K distances. So without further ado, let's take it away.
Thank you so much. Very excited to be here. So, I'm Ibles. I'm a postdoc at UC Berkeley. Today I'm going to be speaking about dark matter. As you can see, the title of my talk is Searching for Dark Matter from Deep Underground, which sounds a little bit of a contradiction, but hopefully by the end of this talk, it won't be a contradiction anymore. So let's start with a definition, right? But we want to know what dark matter is. Let's see what the dictionary says. So according to the Merriam-Webster dictionary, dark matter is non-luminous matter not yet directly detected by astronomers that is hypothesized to exist to account for various observed gravitational effects. This is good, but it's a little bit vague, like various observed gravitational effects. What's that? So let's try to delve a little bit deeper on that. So how do we know that dark matter exists? The first clue came from Vera Rubin and some collaborators, because they were studying the rotation curves of galaxies, in particular the Andromeda galaxy. What you're seeing here is the first ever measured rotational curve. What is a rotational curve? It's basically a way to describe how objects are rotating, how fast they are rotating, as a function of the distance from the center. And the idea is that if you go like farther away from something like a spiral galaxy, you will expect that the velocity of these objects will have to like slow down, because at some point you run out of matter that you can see, luminous matter, and then they go like farther away because of Newtonian dynamics that we've understood for 400 years ago, the velocity should drop. But that's not what they observed. You can see these data points over there. They show a flatness of the curve. And bear in mind that this line over here, surface density, that's telling you what's the distribution of matter that you can see. So you're running out of matter already by that distance, yet your velocity of the object is still like flat. It doesn't like go down. So that really puzzled astronomers back then. They couldn't really figure out what could be causing this thing. So this phenomena has been confirmed with other spiral galaxies since then, and a new paradigm has emerged. Since then, many people have hypothesized that probably what's happening is that that's what you can see in our spiral galaxy. That's what we call the optical bulge or galactic bulge. But then surrounding it, there is this halo of dark matter, an invisible substance that accelerates the objects at the edge of the galaxy, but is not present. You can't really like see it. It's like invisible. So the idea is that you will have like a flat disk and then like this halo of dark matter. And this hypothesis explains beautifully those curves that we've seen previously and that were measured by other astronomers after the 1970s. Now, that's not the only thing that you can explain with the gravitational tensor with rotational curves. I wanted to like show you a quick video that shows if you only had luminous matter in the galaxy, that's how the galaxy would move. And as you can see, it moves very fast in the center, not so fast in the edges. Whereas if you have dark matter in it, and you want to recreate this behavior that astronomers observe, then when you see something that spins much faster. So this is the reality that we're found in like most of pretty much all the spiral galaxies that have been measured up until now. They have that kind of behavior. And the best current explanation we have at the moment is that every single one of them is embedded in this sphere, this halo of dark matter. So a quote that I really like by a science fiction writer, he says that what astronomers always saw and thought was the universe is just the visible tip of a lumbering iceberg of mystery. So let's try to dig a little bit deeper. That's just one piece of evidence. But then over the years, since the 1970s, more and more evidence have appeared across space and time. On the one hand, we have gravitational lensing. These are fascinating phenomena that explains that when you have like a very massive object in between something that is emitting light and you who are observing, light is going to bend. The same way that matter will bend if you just like drop something in like a sheet of in a sheet, like a ball will like bend the surface. The same happens with light. Like light also bends. And using those kind of phenomena, you can try to study objects like this. The bullet cluster is basically a galaxy where two clusters of galaxies collided some time ago. And then here what you're seeing is where most of the regular matter can be seen by X-rays observation, and it's in the center of this picture. But in here, which is like green lights, what you see is where most of the gravitational potential is located. And you can do that by gravitational lensing. You can see that they are like far away. So that means that when these two clusters collided, most of the regular matter, the one that shines, the one that we're accustomed to, stayed in the center, but then that matter passed through each other and went to the edges of the galaxy. Then we have the cosmic microwave background. Let me present you the earliest snapshot that we have of the universe. This picture is the earliest thing that we can ever see in the universe. This was the first time that photons started traveling freely in the universe, and we can see it nowadays. It's like it was basically released 380,000 years after the Big Bang, and to this day, it's still like arriving to us. There are photons that have been traveling through the entire age of the universe. And this map that you can see there, so much richness. Cosmologists and astronomers have been trying to study this map for many years and extracting more and more information. One of the things that you can extract from this map is basically how much matter, regular matter there is, how much dark matter there is, what are basically the fundamental components of the universe. And what they came up with is that there is 5 times more dark matter than regular matter, which is really astonishing. And then also cosmological simulations. The way that cosmologists have fun is that they take a very big box, something like many light years in one side, many light years on one side, many light years on one side. They put a bunch of particles there, let it evolve for the edge of the universe, and then see if that cosmological simulation they created matches known data. Well, what they found is that they are only able to reproduce known data if they introduce dark matter in the same amounts that these guys are telling them. So you can see it's different scales from rotational galaxies, rotational curves that are at the galactic scale, cosmological galaxies. We're seeing the imprints of dark matter everywhere. So what is it, right? Like we're like, okay, so we are seeing lots of clues of what this thing could be, but what is dark matter? So first, let's go over its main properties. Dark matter has to be non-luminous. We can see it, as I said, it's an invisible substance. And that basically means that it does not interact electromagnetically. It doesn't emit light or absorb it. Then it's non-baryonic. This is a technical term that basically what it means is that it's not made of any ordinary particles. And we know that because of some of the evidence that I presented you before, like the CMB and the cosmological simulations. The amount of regular matter that we have in the universe, we call baryonic, is not enough to account for all the effects that we're seeing. Then it has to be stable. Like we've been seeing these effects for the entire age of the universe, which is a really large number, 13.7 billion years. So this means that if dark matter is a new particle, it's a particle that cannot decay, or it has a very, very long decay time. And then it has to be cold. And cold here again, it also has a very like technical meaning. What it means is that it needs to move at non-relativistic speeds. And we know this from the cosmological simulations that I was telling you before. Like astronomers for years have been playing with many parameters, and one of the parameters that we're playing with is the velocity of this new dark matter particle that we introduced. If you put into your cosmological model that particle has very high velocity, then your simulation is not going to match with data. So it has to be cold. Right. So if we know all these properties, then let's look for it. The first place that you will go to look for any new particle to explain the dark matter will be this graph. Let me introduce you, my friends, the standard model of particle physics. So I'm sure that most of you remember the periodic table. That's chemistry. But if you go one level deeper, then what you get is this table. This is basically the fundamental blocks that constitute matter. You have what we call the baryons over here. These are like all the quarks that would make up the neutrons and the protons. You have the leptons, like the electron, which you might know. You combine some of the electrons with two of these quarks here, the up and the down, you form protons and neutrons. Then you start like putting together the protons and neutrons, you create an atom, with the atoms you create a cell, and so on, so on. In the end, you have you. So that's the fundamental particles. We know that there is nothing more fundamental than that. And then these guys over here are what we call the bosons. Those are the mediator particles that basically allow for the different forces in nature to occur. So like electromagnetism, the weak force, the strong force. And the first thing that physicists did when they were discovering this dark matter is that they went here and they went one by one, like trying to, can this be the dark matter? Can this be the dark matter? And what happened is that none of them truly fits the bill that we were looking before. None of them can really explain all the evidence that we have. So for instance, if you try to explain dark matter with something that physicists in a very mocking way call the massive astrophysical compact objects or machos, then you don't have enough of them. So this is basically objects that don't shine. People have hypothesized, oh, maybe it's just planets, right? Or black holes. But no, you don't have enough of them. So you need much more to account for all the effects. And then neutrinos. Neutrinos are a gray particle which weren't discovered so many years ago. These are flying through Earth constantly, coming from the sun and other sources. And they are a great candidate for dark matter. But the problem is that they travel very fast. They travel at basically relativistic speeds. And if we go back to what I said before, that basically means that we rule them out. They cannot be the dark matter. So the standard model is not good. We cannot look there for dark matter. Where do we go then? Well, this is where the job of a phenomenologist comes in. Theorists have so much fun making models of dark matter. And like apparent by the names that they give to these models. Like the Wimsilla, I didn't make that up, like they did. That's how I imagine a Wimsilla looking like. So there are many models. There are the weakly interacting massive particles, the actions, the neutrinos, other black holes. And I want to make a quick point that this is basically how science works. When you don't know what to look for, you make all the kind of like hypotheses that you can make, and then try to search for all of them. You start like ruling them out one by one. It's a very meticulous work until you start like finding some clues of how to move forward.
I can ask a question.
Yeah, absolutely.
Maybe you're going to get into this, but do they what characteristics do they know these candidates have to have in order to narrow down that list?
Yeah, very good question. One of the ones that phenomenologists always try to get right is what we call the relic density. So each of these particles needs to come with a production mechanism. How did you make it in the very early universe? And then how abundant it is with that mechanism that you create. And if that abundance doesn't match our current understanding of how much matter there is, then that's not a good model. So all of those models are already models that pass that test. They actually create that matter with the right amount. But then some of them have the unfortunate property that cannot be detected by any means because, it's like supersymmetry. For string theory, it's like very difficult to detect. Okay, so that leads me to the next section, which is what we're saying before, that there are all these like particles and candidates out there that you could look for. We still don't know which one is the right one. What we know is that after almost 3 decades of looking for dark matter, we know very well how some things are not dark matter. Basically, we've been ruling out things for 3 decades now. So let's go into how do we find it. And here is where now entering into my territory, because I'm an experimental physicist, I should have said that from the beginning. I try to experiment with things in the world to make sense of it. In this particular case, I was very interested in the search for dark matter because there are so many ways that you can look for it. And it can be more or less summarized with this diagram. If you imagine particles interacting, you could have two dark matter particles that find each other, they create some energy, and then because of the famous formula E equal to mc squared that we all know, you can create new particles. You create new standard model particles from that diagram that I showed you before, and you can go and look for them. And that's what experiments like the Magic Telescope in Mallorca in Spain are doing, or some satellite experiments to basically look for the traces of dark matter annihilation, we call it. Then you can do collider searches. Go the other way around. You take two protons and smash them together. And out of that collision, you create a lot of energy. With that energy, you create new dark matter particles, and you try to look for them basically by looking for imbalances of energy. You knew how much energy you put in, and then you reconstruct what comes out. There is something that is missing, and you can be like, maybe I made some dark matter. Let's study the thing. But my favorite is direct detection searches, which is what we do here. This will be what happens if you basically go from the top down. This means you have a dark matter that is scattering with standard model particle, it comes out, and then it gives a kick to the standard model particle. And that kick then gets expressed in releasing electrons and photons, producing some heat in the material where that atom it is, and you can go and search for that. Basically look for a scattering of a dark matter particle of the normal regular atom. So let's look a little bit more on direct detection. As I said here, the goal is to look for low energy scatterings, dark matter particles, with target nucleus site a detector that is deep underground or under a mountain. So in this particular case, I'm showing you a diagram of where the LZ experiment, which is the experiment I work for, is located. This is 1 mile underground, a town called Leeds, and you have these two shafts there, which are basically the elevator that you can take to go underground. There is a lot of infrastructure that has been built in this mine for the past 50 years, or even more, because this was like a gold mine that goes all the way to the end of the 1800s. And then in 2000s, it was refurbished into a scientific lab, and experiments like LC are using it now to make this kind of experiments. Why do we go underground? I want you to remember that. That's like an important point. Here at the surface, there are cosmic rays constantly bombarding the surface. If you try to put your experiment over there, sure, you're going to see a scattering of particles, but many of them you're not interested in. Like, you know them, you know their properties very well, and they're going to hinder your search. So we go underground so we don't see all those cosmic particles, and then we look for that matter. A point that is usually not appreciated is this one, and it's something that I want to remark on. We expect that matter to be fairly abundant in our universe. If you remember that picture that I showed you before, where there is a spiral galaxy, and the way is a spiral galaxy, so we know it fits that model, is this halo of dark matter. So as our Earth is spinning through the center, there's going to be this wind of dark matter passing through. There's a lot of dark matter passing through the Earth. It's similar to neutrinos. We know that there is a lot of it passing. The problem is, how many of them are actually going to scatter? How many of them are actually going to like interact with an atom in your detector and actually leave a measurable signal? And that's where a term like cross-section comes in, which is what we basically measure, sort of using in physics to measure that probability. And that can be very small. So you can have many things passing through, but the probability of any of those particles to interact is very small. That's the important point. Okay, so here's the technology that we use to search for these particles. We're underground, and we have this kind of detector, where we fill this whole bath with liquid xenon, and then at the top we leave a layer of gaseous xenon. Here's a particle coming in. It's gonna create a recall that I said, that kick to an atom in the media. So basically, like a xenon gets like a kick, and then because of that, you're gonna create some heat, which you cannot detect. It's going to release some photons because you excited some of the atoms, and it's also going to release some electrons because you ionize some of the atoms. That first light, we call it the S1. The electrons are immediately drifted up because there is a high intensity electric field applied in the whole chamber. These electrons go to the top and are extracted into the gaseous phase, and then they are accelerated further to the top. And because electrons now are traveling through a gaseous phase, they produce a second flash of light. That's the S2. why these names, which I know sound very boring, S1, S2, but they're important. You basically detect these two light signals because this detector, what it detects is light. These guys that you see there, they're basically objects. They're called photomultiplier tubes. They turn light into an electrical signal, which you can measure very precisely. So you have the S1 and S2. Because of the array, you can reconstruct the XY position of where the interaction happened. And then because of the time difference between the S1 and S2, even though these electrons move up at a constant velocity, you can reconstruct the depth of where that happened. So this technology, which has been perfected for the past 30 years, now have an incredible resolution in position. You can reconstruct particles happening at the millimeter level in a detector that is 1.5 meters wide and 1.5 meters tall. The same for energy. You can measure single photons or single electrons being released in the detector and then reconstruct their energy very precisely. So
Do you detect this one?
do you detect this one?
Do you
Yes.
also detect this two or both?
No, both. And then with both of them, you're able to reconstruct the depth of the particle.
So in S1, there's like some photons being emitted that travel faster than the electrons. You detect those before. Then
Yeah.
When the electron reaches the gas space, it emits some other photons that then emit faster.
Exactly. So I should have made that point clear. Photons travel at the speed of light, so you basically see them immediately as the interaction happens. But electrons are going to have a delay, travel up, and then you have the second flash, which again you detect immediately. So there is a time delay between the two. All right, so this is more or less how the technology works. And then we use it in this experiment called LZ. You might remember that picture that I showed of one of the shafts. Now here you can see a real picture of it. This is the Gates trap, that's the Ross shaft. And this is a picture taken in 2019 when we were moving basically the TPC, this object that I show you here. So the actual one that we used in LC, that's when we were moving it from the surface underground. So as you can imagine, there was like lots of tension like during this operation because you don't want to like jam your car and like break it or something like that. There's many years of like research that have gone into like that. So LZ is located in the beautiful Black Hills in Salvador. I don't know if you've been, but it's like a gorgeous place, really nice. And it's one mile deep, so like very deep underground. It takes about 15 minutes to go all the way down with the shaft along down. And this is how the TPC looks like. And I keep saying this word, so TPC basically means time projector chamber. That's the name of these kind of detectors. And you see, it's like beautiful. We have these layers of PTFE panels, which is basically a material that is very reflective. So from the inside out, if there is any light being emitted, it's gonna reflect like all the walls, and you're gonna lose any of the photos. You can like see like a single photo in the middle. And then it's, as I said, 1.5 meters tall, 1.5 meters wide, and it contains 7 tons of liquid xenon. Let me say that again. So in kilograms, that will be 7,000 kilograms. And this by far was the most costly part of the experiment. Because back in the day when we bought the xenon, it was still at a reasonable price, a bit lower than that. But now, because of the war with Ukraine, because like shortage, because other industries are using xenon increasingly, the price of xenon has skyrocketed. So for future experiments, like sometimes it's kind of like now a really hard time thinking how we're gonna like build the next generation experiments, given that the xenon is so expensive.
There's a question from the Zoom asking what temperature or other measures must be taken to keep the xenon in liquid form?
Oh, that's a great question. So this has to be at what we call cryogenic temperatures. Particular, that's minus 111 degrees Celsius. So very cold. Because xenon is a noble gas. That means that the regular, like the standard temperature is going to be in a gas form. So you need to bring it all the way to minus 111 degrees to have it liquid. Okay, so you can see here how the TPC actually looks like. Yeah, go ahead.
The walls being reflected, yeah, like in the diagram we showed before, it was in like they all travel straight to the detector, so that was nice. But if they are bouncing, then how do you know how like what distance it took? If there's only one photon, you don't know if it went straight or if it went around and bounced on the wall.
Yeah, that's a good question. Those are the electrons.
Those you know they travel straight.
Yeah, and the reconstruction of the position, you always do it from the S2 signal. The electrons get to the gas, then they are extracted, and then there is a very thin layers, like 8 millimeters, where they can emit light, and then all of a sudden, like, poof. So what you see there, it's the pattern of that guy, not this one. So there is no possible reflection that can mess up with your XY position. You will know it quite precisely.
I see.
But in terms of measuring the amount of photons, you still care about capture it by collecting every single of them. You're not going to use it to reconstruct the position, but for the energy, it's very crucial. You're able to reconstruct to collect them. Does it make sense?
But does it matter that like from the, I guess like how many photons are you expecting to be produced in one of these events in S1?
Depends on the particle that you're interacting, but could be anything from 1 to 50.
And like, does it matter if it goes like kind of straight up or if it like bounces in the walls for like, you know, some time and then it ends up?
No, because of what I said. What you care about is the accumulated charge that you integrate for the S1 signal after that very short pulse. So in the end, all the photons that you're collected is going to be basically accumulated in what we call here this pulse, like that amplitude. So as long as you collect all of them and you integrate the area, then you have basically your S1 signal.
So the idea is that they go so fast that no matter how many times they bounce, you're gonna collect them all, you know, such a short amount of time compared to how long the electron takes to travel up.
Exactly. It doesn't matter if it was this PMP or that PMP that reflected it. At some point, you integrate over all of them and you reconstruct the energy of that particular interaction. Good question. Okay, so one important piece that I didn't mention is that here there is a diagram of the ELSE experiment. Here is the TPC. We've been talking about for quite a while. But a very revolutionary idea that happened with the previous generation of the experiment, which was the LUX experiment, is that we created kind of like onion layered experiments. We have this one, the one with the xenon in the middle, but then we have something called the xenon skin, which is just a like very thin layer of xenon in the outer edge that is instrumented. So it also has like these PMDs that can detect light. And then here in green, you can see what we call the outer detector, which is a tank full of a liquid that shines a lot if a neutron is captured. And then you can measure that light with those big boys. Those are also PMPs, but very, very big. You don't care so much about them being small. So the idea is that if there is any particle that we understand very well, like gamma particles, neutrons, muons, they are gonna interact once inside the detector, but then another time in the skin or another time here. Like you can have like multiple interactions. And by detecting them more than once, you can veto them. You can say that was not a dark matter particle that caused the interaction, because we know that dark matter interacts so infrequently that you're gonna get at most one interaction. Because more than one is most likely a background particle, which we're not interested in. So that was like a big kind of like idea that was developed some years ago, and now basically all the experiments in this area like use very useful. All right, so we switched on the experiment in 2019 after more than 5 years of design and construction. Here I put the little joke that was basically the duration of my PhD. I didn't see a single real piece of data while I was doing my PhD. But then I moved here. And now here at the postdoc, the first thing that I did was like actually analyze some real data from the experiment. So that was very exciting. Then COVID happened, and that hindered the activities of LZ, as you can imagine. But in the summer of 2022, we finally did our first data release that came with some companion papers. Here I just put a screenshot of the live stream that we did, which was watched by lots of people. It was very popular. It was a really nice thing. So now after 2 years, we're expecting to do a new data release that should happen this year, probably this summer, we'll see. And then the experiment is expected to continue operating until the end of the decade, 2028. All right, so here's some pictures to, again, like drive home the message of how complex building such thing underground is. Like my previous advisor from London, when I was doing my PhD there, gave the analogy that this is like building a spaceship. Once you like seal the whole experiment, it's gonna be like super hard to access it, especially because of this like onion structure that I told you. So you need to be very careful with your planning of how you're gonna build things. We need to be super careful with the cleanness of this experiment because something like dust contains a lot of radioactivity that we're gonna see in the detector and it's gonna affect our measurement. So that's why when you're building, you always have to be in a clean room, wearing like these lab coats. Transportation underground was done in a very meticulous way. And then when everything was done, this was a ship that I took for 2 months in the summer 2021 to basically fill the outer detector with that liquid that I told you that was very good at capturing neutrons. That was a very fun experience. That meant that every day my work was to take the shaft, go underground, be there for a while, do some science, and go back to the surface. And it was like very simple life, but with a very clear purpose. All right, and I'm not gonna go through any of these, obviously, but I just wanted to show you what looking for that matter looks like in the real world, because we've been talking a lot about like these diagrams and it's good like to get a sense, but in the end, what we do is this. We publish papers where we're basically placing constraints for models of dark matter. That long list that I showed you before, some of them are actually here. So that's WIMZilla, ultra heavy dark matter. These are actions, WIMPs. These are different models that what we do is that we've taken data for some time. We did not observe anything that is compatible with that model being true. And then what you can do is you draw a line in a parameter space and you say anything above is excluded. If the dark matter particle had this property, like a property over there, we would have seen it. And there would have been an excess of data, but we did not. So you can put a line and tell everyone else, don't look there. And that's what the game that we've been playing now for quite a while, adding more and more constraints of what dark matter could be. That's what I really mean by that sentence that I said before, that we've become really good, recently good at ruling out what dark matter can be. And that's good, that's how science should go, giving us direction. So I'm probably over time, so I'm just gonna like quickly wrap up with a personal statement. I wanted to finish with giving you my personal view of why I think dark matter matters. First, I want to say that just because we're doing like these fundamental searches, this is the production of new knowledge. This is what we've been doing for millennia. We're very curious beings. We want to know how the world operates, and searching for dark matter is yet another example of trying to answer the question of how we came to be. Dark matter has played a very important role in shaping how our galaxy and ultimately Earth was formed. So we want to know what it is and you know how it's like playing in other parts of the universe. Then also that we're training the next generation of researchers. Doing fundamental science is hard, let me tell you. Like there are many questions that we scientists obsessively think about, oh, it should be this, and there are like many details you need to go through. But by working through this process of trying to uncover something hard, it's a big hub of innovation and new ideas, and people really like, you know, get trained with great skills that they can apply to other enterprises. And finally, fundamental science is a great way of fostering international collaboration. We're in an ever more divided world, and I believe that science can really be a way to unite us. A diverse workforce is going to drive innovation and is going to create more bridges between nations. Here I wanted to put the example of CERN, which was founded soon after World War II, and since then has been really a model of how scientists from all over the world, were coming from nations that have had like big fights between them, can really work together for a common cause and advance science. So please take this home. If you need to remember anything from this talk, is that one, there are many pieces of evidence from small to very large scale that support the existence of dark matter. You might read sometimes in the news, dark matter is fake. We don't believe that dark matter is real. That's because sometimes some people can find that they found some model that they don't need a dark matter particle to explain that. But most of the times it's like a very narrow explanation. It cannot explain all the plethora of evidence that we have. Only assuming that it's a dark matter particle at the moment does the job, explaining all the evidence. So we don't know what is yet, but we're becoming increasingly good at trying to like rule out more and more like things that could be. So hopefully at some point we'll strike both. That's the hope here. There are many ways to search for it, and as I said, you could basically categorize them in like three main ways. So think about calendar searches. You try to produce them within direct searches. You try to see the traces of dark matter annihilation, and with direct detection, you try to see the kick of a dark matter particle of a nucleus. And then for this direct detection, xenon-based detectors like LC are lead. I'll leave it there. Thank you very much for your attention. Absolutely.
The space between, when you look through the stars, and you see the star and then black, is that considered dark matter?
No, that's a very good question. That's just empty space. But dark matter will be very there. It's just that, with dark matter, it's an invisible substance, so you will never be able to see it, but you will be able to experience its gravitational effects. Please.
Why is it important to know the position of the collision very precise?
Yeah, because again, the game we're trying to play with these kinds of detectors is to reject known type of particles, which we call backgrounds, and see that on top, and see an excess of particles, we will call the signal, on top of that background. So knowing the position can make you have like more information to distinguish between those like background particles and the signal particles that you're looking at.
Yeah. Oh, sorry. You can go first, and then we have some questions on this.
Why xenon and not any other novel gas like helium?
So happy that you're asking that question. So xenon has this great property that we call self-shielding. It's a very dense atom, and when you put it in liquid form, it's like a very dense state. So you can basically create what we call the fiducial region. We look back to our full detector PTC. If this is full of xenon, you can define basically a region around, which we call the outside of the fiducial region, where you're gonna basically reject that region and not take into account when you're doing your analysis. Why? Because one of the most radioactive and dangerous parts of the detector are the walls. The walls emit a lot of light, but those particles cannot come inwards a lot because of how dense xenon is. So that's why you can just place kind of like a fiducial, you lose some of the xenon, but that's fine, because then you have a very, very quiet region in the middle. And it's only xenon that has that property. If you go to argon, people are trying to experiment with argon as well, but they are not as sensitive because of that.
So you would need like a way bigger chamber because of the
Yeah.
Okay, and then, we have a few coming in. So the first is asking, how does your experiment differ from the drift experiment in Northeast England?
Yeah. So we have a knowledge member of the audience. That experiment is basically trying to look for the annual modulation of dark matter, which is something that I didn't talk about. Another way that you can search for dark matter is to think, okay, so you're telling me that we have the Earth that is traveling, spinning around the center of this galaxy. You will have this like wind of dark matter that is coming through
because
I'll try to like throw it here in the camera. Because sometimes
Oh,
you
I
have
see.
okay, good. Well, because sometimes you have your air that is going towards the wind, sometimes away from the wind. The idea is that there should be some seasonal variation in the amount of dark matter that you're detecting. And people have been trying to search this for a long time. And the big drama that we had in our field for a long time is that there is one experiment that has claimed that is seeing this for the past 30 years. I kid you not, they published a paper in the 1990s and they're sticking to it. They said that they found the dark matter and everyone else is wrong. The problem, as you can imagine, is that everyone else is not being able to reproduce their signal. there is still like that little controversy. So drift is yet another of those experiments that is basically trying to reproduce that signal that this other experiment, Dama, measured many years ago of that modulation of the dark matter.
Thank you. Our second Zoom question is, while detecting dark matter would be a great achievement, would it necessarily help you to explain what the particles are? Like, if you can detect dark matter, how will you then know kind of what that dark matter is?
Yeah. So what I think that question is trying to get at is that what we know about dark matter requires the indirect evidence. We know already a lot about what gravitational effects it has on regular matter. So when I talk here about detecting it, I'm already like talking about that second part of the question. Like when we detect dark matter in this way, we will know what it is, because this is already like trying to look for the particle that is creating that kind of signal. There might be a misconception of what dark matter really is like. What does it mean, like interact? Here, this kind of detection, that's already like assuming, okay, we know about all the gravitational effects, but we're not gonna bother about them. We're gonna like wanna try to like measure very precise properties of the particle that creates that dark matter.
Thank you. And then our final Zoom question is, if dark matter doesn't absorb light, what happens when radiation dark matter?
Well, it just like doesn't receive it. Like there is no scattering of photons from dark matter or anything like that. There's no mediator particle between a dark matter particle and light.
Okay, great, thank you. I think that's all Zoom questions done. And then if there are any more audience questions, we can maybe take one more, and then you can hold them until after the next.
Please go.
Is this like the neutrino detector, or is it the same thing?
Yeah, very good question. So in that same place where LZ is located in South Dakota, there was an experiment in the 60s done by a scientist called Ray Davis that discovered the neutrino for the first time. And back then, they also didn't know what neutrinos were, and they were very puzzled about certain measurements they were making the sun, and the neutrino was the key element that they needed to find. But since then, we know the neutrino very well. Like by now, like neutrinos are actually a background to dark matter searches. We don't want to see neutrinos in our detector, but we do constantly. So it's a similar kind of technology, but we understand the neutrino very well by now.
Thank you very much for a great talk. I think if there are any, lingering questions, our speakers will hang around, so you can ask them later. But for now, we'll introduce our second talk, which is Ryan Hoque. He's a final year computer science PhD candidate and robot learning researcher, advised by Professor Ken Goldberg here at the Berkeley Artificial Intelligence Research Lab. He's a Bay Area native and a lifelong Cal Bear, so he was here for his bachelor's and his master's in engineering, electrical engineering and computer science, and is still here for his PhD, so we're lucky to have him. Outside of work, he enjoys philosophy, basketball, and playing the piano, and we're very excited to hear you talk today, Ryan, so thank you.
Okay, thank you. All right, am I like in frame? Yes, okay. Yeah, thanks everyone for coming out. So today I'm going to be talking about something called, I guess this guy's.
You can click more,
Oh, okay, more.
and it's like hide.
No, high floating, okay, great. Great, okay. We're talking about some imitating intelligence and the quest for a mechanical mind. So this is, of course, an AI generated image to be on brand of a robot trying to imitate a human. And yeah, I'm a PhD candidate here at Berkeley. So this is kind of an ancient quest. This started, since antiquity, when Aristotle was pondering this question: if every tool, when ordered, or even of its own accord, could do the work that befits it, then there would be no need either for apprentices for the master workers or slaves for the lords.
basically saying if machines could just, do the thing that they're supposed to do by themselves, either we end up with a post-work utopia or a Terminator-style dystopia, and the jury's out on which one will happen, but that's the hope. And the first robot in like public consciousness or the sphere of human imagination is also from Greece. So this is from Greek mythology. There was a robot called Talos, which was said to be made by the god Hephaestus, the Greek god Hephaestus, which was this giant bronze automaton that was defending the island of Crete from like pirates and things like that. So the idea of robots is very ancient too. Now there's a more modern take on this kind of idea, and this comes from Alan Turing, who was some regarded like the father of computer science. Right when computers were starting to become a reality, he published this very influential paper called Computing Machinery and Intelligence. And the opening line is, I propose to consider the question, can machines think? Right? And through the course of this essay, one thing that he proposes is now known as the Turing test. Right? The Turing test is a proposed test for how do you tell, say a machine has achieved intelligence, how do you tell that it is intelligent? And what he proposes is that you have the machine behind one divider, have a human on the other side, and then you also have a human judge. And then you give the human judge, basically allow it to talk to both the machine and the human. And if you can't tell which one's machine and which one's human, then it has passed the Turing test for intelligence. And originally, it actually wasn't called the Turing test. Originally, it was called the imitation game, right? So imitation is like a theme that I want to focus on today. And essentially, what's going on here is the machine is going to try to imitate the human so well that another human is going to get fooled, right? So there's a paradigm in AI and robotics that we call imitation learning. You see this baby is trying to imitate Rocky, right? And it's something we humans do. We learn from teachers, parents, mentors, peers. Basically, it's learning from human examples and feedback, and it's one of the dominant paradigms for how do you train an AI, right? The other dominant paradigm is reinforcement learning. So Pavlov's dogs was a popular instantiation of this. It's kind of like taking this idea of classical conditioning and applying it to robots. So you say good robot or bad robot, and eventually you'll learn behaviors that get more good robot signals, hopefully getting something useful, right? So broadly speaking, these are kind of the two dominant ways that we train robots and AI today, is imitation and reinforcement. So if you see like a Waymo in San Francisco or something, all those self-driving cars are primarily using imitation, in that a lot of humans drove cars. You collect a gigantic data set, and then you try to imitate how the human drove that car. You try to imitate the steering, the acceleration in these situations. Whereas reinforcement has been very well suited for things like games. So famously, AlphaGo defeated the best human player in the world at Go back in 2016, I believe. Reinforcement learning is very good at these kind of structured settings, less good at the unstructured real world, where most real world robots, for the most part, that you see that are functional, are going to rely on imitation, right? Though there are caveats to that, but broadly speaking. Okay, now if to complete my taxonomy of relevant terms here, there's another term that gets thrown around, which is like supervised machine learning, right? Whenever you hear machine learning this, that, there's supervised and unsupervised. Primarily, they're talking about supervised. What does supervised mean? It means you have a big data set and you have labels for each data point in your data set that was given by some human, right? So ImageNet was the first breakthrough here back in 2008, where there was a data set of 1 million images, and we had people go in and label, what is this an image of? Is it a dog? Is it a cat? Is it whatever? And once you have this data set, you can learn a mapping from the data to those labels. And then you start to learn things that are useful. You can automatically say, this is a cat, this is a dog, because I've seen 1,000 examples of this, right? So here you can see this is very connected to imitation learning. Arguably, it's kind of like the same thing, different applications of it, where you have data from a human and you're trying to imitate what the human would do, right? Now, what happens when you do supervised learning at internet scale, right? You scrape the entire web, you get everything a human ever wrote or took a picture of and put on the internet, and you get kind of amazing results. So ChatGPT is exactly trained in this way. All these other large language models, large vision models, Gemini, Claude, DALL-E, Diffusion, they're all relying on the same exact idea, which is that, you know, we have all this intelligent human data. Let's just imitate the patterns in that data, and what comes out is going to be intelligent, right? And this really took off, say, like last year or so. Fun fact, the main architect behind ChatGPT was a Berkeley PhD as well. So there's Berkeley ties to everything AI. So this is really interesting. Now we can ask, okay, what if we do this for robots, right? So this works for language, it works for vision very well. Can we train a robot to, like, you know, fold clothes, do our laundry, whatever? Can we apply a similar recipe? So where would the data for that come from? So that's something called teleoperation. That's essentially the idea of remote control. So you see this human is operating these two joysticks or whatever it is, and the robot is directly copying exactly what the human is doing. So this is imitation in the most literal sense, where you're exactly replicating what the human is doing. And when you do this, you're capable of incredible dexterity, right? You can assemble this board here, you know, at a level that autonomous robots can't do yet, because the human is telling you what to do. So this was from 2023, but this has also been the case from decades, right? Even in 1957, we had a similar kind of leader-follower system that can, you know, light someone's cigarettes, and you have someone behind the scenes kind of puppeteering this robot system, right? So teleoperation is very capable. Even before 1957, Nikola Tesla in 1898 first demoed this remote-controlled boat that was controlled by radio, and Goertz in 1949 demonstrated a similar kind of leader-follower system for clearing radioactive material after World War II. So it's useful to distinguish between these notions of what you could call a tele-robot, like a robot that's remote controlled, versus a robot or autonomous robot, which is doing things by itself, right? Now, what happens when we just apply, you know, the recipe, supervised learning, collect a ton of humans doing things, train a machine learning model on it? So this would be imitation learning or robot supervised learning. Why would you want to do this? Well, you don't want to exactly replay what the human did, because you want to be able to adapt to new situations. Say, like, you know, something's a different color or something moved in a certain way. You don't want to be exactly repeating what you did, because you won't be able to do it. Now, the problem is, what happens in these cases is you get something known as distribution shift. What happens is, because the robot is actually executing its actions in the world, doing things, you try to imitate what the human did, and you got a little bit of approximation error, perhaps. You're like a little bit off. And then you do it again, you're a little bit more off. And now this error starts to compound, and quickly the robot can visit states that the human never did. And once you do that, you're kind of at a loss for what to do, right? For example, say you want to clear a mug off a table. If the robot accidentally knocks the mug down, nowhere in the human data did the human knock the mug down, so now it doesn't know how to pick it back up. That's a concrete example, right? So this is something called distribution shift. There's also a data problem, right? So we have this kind of chicken and egg situation in robotics, which is that robot learning needs giant, large-scale data sets from robots being deployed at scale, and yet robot learning is not yet reliable enough to be deployed at scale. So how can you resolve this paradox, right? We're not fortunate enough, as language and vision were, to have the internet lying around to let us, you know, copy it, because here we have to do all that teleoperation stuff, right? And someone once made an analogy that the internet is kind of like fossil fuels, where we got lucky and they happened to be under the ground, and then we used it and developed all this energy stuff. We're not as fortunate for robots. So what my PhD research has focused on is trying to answer this question of, can we reliably deploy these robot learning systems today and at scale, right? And I'll kind of blitz through the ideas here roughly, but probably what the main tool we're going to use is something called interactive imitation learning. So it's imitation learning, but control of our system is going to switch between robot and human. in an intelligent way. So when this robot encounters some state where it has distribution shift, where it hasn't seen reference behavior, it can come in and say, can you come help me? Human, come over, show me what to do. Add that to my data set. Next time I see it, I won't make the same mistake. So this is kind of the idea of supervision on demand in some sense, where the robot can even, send a push notification or something. Human sees it, says, okay, I gotta help it, right? Of course, this begs the question, when should the robot actually ask the human for help? And it turns out that this is a very difficult question to answer because it's kind of like an unknown unknown where the robot doesn't even know what it doesn't know, right? It's like not modeling that, right? So there's a few works in this line of work. One of them we worked on was called Thrifty Dagger. The idea was, I'll gloss over the details, but we estimate these two quantities, the novelty and perceived novelty, perceived risk at a given state of the robot system. We seed control when they're above some thresholds. The upshot, though, is that if you do it intelligently, if you answer your question of when to ask for help in a good way, supervision on demand can be as effective as if a human was constantly supervising the system and then remote taking over when it sees that the robot's doing something wrong. Which is kind of amazing because one of them requires the human to be watching the whole time. The other one, the human can go do something else. Robot can come in and say, I need help, right? So in both in terms of autonomous success rate and supervised, where the team is working together, this can be the case. And also how much of the episode, or we call this episodes, rollouts, how much of it is the human controlling, right? So while it's learning, it's maybe asking for help roughly 25% of the time, both in if it's human and robot supervised. But then after learning, this really dramatically falls off to say 1 to 5% because it has learned to not repeatedly ask for help in the same situations that it had before. There's another notion of supervision on demand, which is remote supervision. So the internet is mature enough that your human supervisors don't actually have to be physically present, right? You don't need the guy right behind the robot telling you what to do. You can actually do that over the internet, and that could be anywhere in the world. So one example of this was a project we did with Google DeepMind, where they had this remote robot work cell they were trying to pilot. We were in Berkeley, they were in Mountain View, and they were forwarding us all these camera images of their work cell at different angles, and we were sending back basically actions for the robot arm to take in a closed loop control loop at 10 hertz, right? So this was something that's very doable today. It was pretty reliable. So it's not, science fiction. So we have this in the case of, the single robot, single human. Now, what happens if we generalize this? Right now, it's a real mess. Now we have, a pool of humans that could help us. We have a whole fleet of robots. That term comes from like a fleet of ships, but you usually call it fleet of robots. How can we help, do the optimal human to robot allocation so our whole fleet is doing this thing the best way it can? Amazingly, when we looked at the literature, no one had even studied this problem or formalized it. And that's despite the fact that we see this all the time in industry. So it turns out that the secret to getting these Waymo cars working on the road and your warehouse automation, your self-driving cars, is often they're going to fall back on humans in the edge cases that they don't know what to do. They're going to say, someone come help me, and the remote controller is going to come in and that's going to be concealed from you, the passenger. And it happens less and less, but the same idea is happening here. So despite the fact that people are doing this industry to deliver reliability, there wasn't a systematic study of this in academia, right? So we had a follow-up paper the following year called Fleet Dagger, Interactive Fleet Learning. The idea here is we're going to formalize the setting of interactive imitation, multiple humans, multiple robots, right? So some allocation policy that's automatically going to assign our humans to the robots that need the most help at any given time. That data is going to go back in, the whole fleet's going to learn from it. And we want to find what is the optimal allocation here? What's the best way to do this? Now, in order to evaluate this, we ran simulations, we ran physical experiments. In simulation, what we did is we can run 100 or even 1,000 or even 10,000 robots doing things like manipulating cubes, navigating around, like running around kind of in a goofy manner there. But what's going on is this is built on something called NVIDIA. Isaac Jim is a software from NVIDIA where they use their GPU, their graphical processing unit, to accelerate physics by like 10,000x or something. So you can basically simulate this very effectively these days. This came out maybe like 2 years ago, and you couldn't have done that before. In physical, we don't have the resources of a Google or something like that. So what we did instead was we repurposed these two bimanual robots that we had. We have two labs here at Berkeley. They're roughly a kilometer apart, but we repurposed these into 4 individual robot arms, where each robot arm doesn't know about the other as much, and they're all doing the simultaneous block pushing experiments. Doesn't look like much, but basically what's going on is it's imagining it wants to push to this goal region, it pushes there, once it reaches there, it'll reset it and try to learn to do that over time. And when it needs help, remote humans can come in and operate it. Okay, so now let's take a step back. Outside of this research, let's look at the field as a whole. So now you can't go outside, or you can't turn on CNBC without hearing AI, robotics, AI, GPT, whatever, right? AGI, whatever. So there's a lot of hype going on. And this is a concept that's been around for a while, the AI winter, where when AI is going well, we have an AI summer, and then it doesn't go as well as we thought, and then we have an AI winter, and then the VC dollars dry up and so on. And this happened several times throughout, in the 70s or something, it was like expert systems was like all the rage. It's like, oh, this is gonna solve everything. The problem is that AI is this really like fuzzy term that can mean kind of anything. It's like, oh, if AI works, then we have an artificial human, you can do anything, but that's not how AI actually works, right? So if you have more understanding of like the limitations and how it's actually working, you'd have a better idea of this, right? So I would argue we're probably here. Like, right? Maybe I could be wrong, but I think we're like, we have a lot of inflated expectations after GPT and generative AI kind of took off. Perhaps we're going to eventually realize it doesn't live up to all the crazy things that we think it's going to do, but eventually things will be left behind and we'll have productive output, right? So one instantiation of this recent wave of AI funding is humanoid robots are taking off. Actually, NVIDIA had a big announcement yesterday. This is a robot from Tesla. It's called Tesla Optimus, and it's folding a t-shirt. And you have what a humanoid robot is doing is you have a robot that has a human form factor, human-like hands, kind of human-like motion, human-like legs. The idea being, if a human can do it, a robot should be able to do it. Now, what this Tesla bot is doing is actually, it's not controlling it itself. There's someone behind the scenes who is teleoperating it, right? So this is what I mean when I call it's like a Wizard of Oz demo. Like the Wizard of Oz who is behind the screen, telling you what to do. This is not possible autonomously yet. And remember, teleoperation has been working for decades, right? So I would say with the things you've learned through this talk, I would bring a critical eye whenever you see some hype demo and see, to what are its limitations, what is it actually capable of. Be careful about these demos. These demos drive a lot of funding, drive a lot of markets moving and things. So of course they're going to be cherry picked and so on. That being said, it's very amazing hardware. You can see it's very fluid like motions. And there's definitely, you can try to do supervised learning on that, which is what they're doing now, but not there yet, right? There's another demo from Figure AI. This robot looks straight out of a sci-fi movie. Very cool. I saw it a few weeks ago. This guy was showing me around. But what it's doing is it's clearing up this table with dishes and cups. And you want to pay attention to what's going on here, right? So this is better in that it's actually autonomous. It's doing it by itself. It's also at 1x speed. That's a big thing. Sometimes demos are slowed down or sped up, I mean, because robots are often slow. This is in real time. I would watch this if you have the chance. You can talk to it with GPT and it's like answering you is kind of eerie and creepy, but it's also really cool. But again, think about, this is probably cherry picked, right? If the cup's removed a little, would it still work? Like, is it overfitting to this exact example that's in front of it? Hasn't seen this 1,000 times? All questions that you should ask. And this is also working with imitation learning, with supervised learning, right? The dominant way to train these things. Okay, so last kind of topic I want to talk about is just broadly, philosophically speaking, right? When we look at GPT, we look at AI systems, you can ask, how intelligent are these things, right? You can recall the Turing test, right? Does it pass the Turing test? These systems these days are quite good. They actually might, right? You actually might be able to talk to ChatGPT and one a human on the other, and you might not be able to tell which is which. Does it matter that it passes the Turing test? Is that a sufficient condition for actually having human level intelligence? I would say perhaps not, given the light of things, but there's also the case of the moving goalpost. Every time something shows, something's intelligent, you say, oh, that's not intelligent, it's actually this other thing, right? There's a deeper question, which is it actually intelligent, or is it the mere appearance or imitation of intelligence, right? Is like imitating an intelligent system itself intelligent, right? So people sometimes call language models stochastic parrots, random parrots, or whatever, in that they see all this data, they're just echoing what they've seen in the data. They're like parroting, you have the whole internet behind it. You don't know what it's seen and what it's not seen. Chances are it's seen everything, right? So now it's just repeating something it's seen. So, would you say parrots understand the English language? Perhaps not. Maybe they're just repeating it, right? Are we good judges of this? Like, we are very smart people can be fooled by a seemingly intelligent haiku or whatever it is, right? Because it looks like what a human would produce, right? But are we even good at judging what's good at that? In particular, if robotics is so far behind, where like we can't fold a t-shirt yet with a robot, how good is AI, right? Because evolution took the other path. Evolution evolved movement, perception, before we'd had language, before we had symbolic reasoning and things like that. It seems like AI took the opposite approach and kind of went the other way, right? Okay, there's deeper questions here. This is the Tin Man from Wizard of Oz. What if we flip the script here? Is it the case that intelligence itself is just mimicry? Is it just imitation? Are we parrots? do we, so this is something called like mimetic theory, mimesis and things like that, where, to what extent do humans just copy culture, peers, tradition, whatever it is, rather than come up with original things? Are you combining existing ideas and repackaging it, right? And the other question we could ask is, okay, we're trying to build this mechanical mind or elevate a machine to human-like status. What if we flip that question? To what extent is the human brain just a biological machine, right? This hypothesis has been considered at least since 1747. L'homme machine, man a machine, in France was arguing this point. So I'm not going to claim I know the answers to these things. I'm just putting that out there, food for thought, maybe unsettling, but perhaps. The thing I want to close with is this beautiful scene from actually New Zealand, right? So when I went to New Zealand a couple of years ago, I went to this glowworm cave where it's called the Waitomo glowworm caves. If you go into these caves, you can take a boat through these underground caverns, and on the ceiling you're going to see all these glowing worms, these worms that produce light. It's this really beautiful scene. And then you ask the tour guide, like, why? How is it even possible? Why is this happening? And the answer is that flies will wander into these caves, and they're going to mistake the glowing ceiling for the night sky, and they're going to fly over there trying to navigate with these stars, bump into the worms, and the worms are going to paralyze them and eat them alive. So it's very morbid, but it's still very beautiful in that, like, nature has somehow, these worms have never been outside, right? They have no understanding what the sky is, but because the flies have an understanding what the sky is, nature has optimized these creatures to imitate the night sky in this kind of amazing way. So yeah, that's my talk today. Thanks for your attention. Happy to take any questions.
Yeah, I think you talked about how reinforcement learning was like the game of Go, right?
Mhm.
So reinforcement learning was good for applications that were game-like, but maybe not so good for the real world. But why is that the case? Because like you can imagine this like block problem. It kind of feels like a game you could attribute some sort of cost function.
Yeah, definitely. So I put a caveat on that because RL is starting to work in the real world. where there's actually a biped robot walking around Berkeley. You might see it. There's like a humanoid bipedal walking robot that was trained entirely with reinforcement learning. So in simulation, they basically showed it all these different variations of terrain, had it adapt to all those variations, and then they put that exact policy straight onto the robot system, and it worked. It's kind of amazing. So what happens is here is if you can model like the diversity of the world in simulation in a game-like environment, and that's like sufficient, then it can work. Or if you're like two strands of thought here. One is manipulation, where you're moving things, folding t-shirts, whatever. This is a very basic manipulation problem, and RL could work here. If you're like folding t-shirts or something, you're trying to change the state of the world to some desired state. Versus when you're doing locomotion, you're reacting to the world. You're kind of like a blind system. You get some input and you're like, oh, I want to adjust myself to that. To the extent that you can model your state, you can do very well with RL. But once you have to start modeling the state of the world, perceiving it, understanding it, that's when it gets tricky. Now, the other thing with RL is that basically how it works is it'll randomly do something, see what was the effect of randomly doing something. If it did pretty well, it'll do it a little bit better. It'll just kind of randomly move around in action space. So when your action space, like the space of possible actions you could take, is like not too big, then you can explore that very efficiently in things like games. Problem with the real world is every time you move your robot arm, there's like infinite ways you can move it again, and then infinite ways you can move it again, and so on. Like there's this exponential ways of things you could do something. So the chance of randomly going and like picking up my cup and placing it where I want it to be without any kind of human intervention is very tricky. So that's in the limit of infinite time, you probably could find it, but or a really fast simulator, perhaps. Yeah. NVIDIA's hypothesis with the robotics is they're going to simulate the whole world and it's going to work. So it hasn't worked yet, but they're trying.
Yeah, a conflict of interest.
Yeah, yeah. Yeah.
In thinking about these robots, like what applications do you see as the most important?
Like, do I have to care about feasibility or just like
I guess
terms?
I guess it's more just like, of the people you work with yourself, like, what when you're like building these models, like what are the things you're hoping it to do?
Yeah, okay. So the white whale of every roboticist, for the most stated at least, is that we want to achieve human level dexterity in robot systems. And whatever a human can do, like manipulate your phone whatever way you want, like not drop it, and so on, to have a robot that's just that good at that thing. Because then what you could do is you could automate any kind of like physical laborious thing that for the most part humans don't want to do. That they do it because they have to. But the goal of robotics is in some sense to take the robot out of the human, let the human do stuff they actually want to do rather than bagging things all day or whatever, repetitiveness, dangerous tasks, things like that. So that's the goal. We're not close to that goal yet because dexterity turns out to be really hard. Something called like Moravec's paradox, where what's easy for robots is hard for humans, what's hard for robots is easy for humans. Or the baby will effortlessly do the kinds of things a robot couldn't imagine. But I think that's the needed goal. And then the goal of that would be either you have a home robot that's doing all your chores for you. That's what people always ask for, like, oh, when's my robot butler coming? And it's like, give it a few years, give it like 20 years, maybe. Because right now we just have a Roomba, like it's not doing anything that interesting. But it'd be really nice if it could clean your house, do your laundry, cook your meals, and so on. And you could also put it in factories. You could put it in space. You could, do all these kinds of things.
Do you mind if I ask a quick follow-up?
Yeah.
Do you ever think about a world in which humans actually want to do these tasks you think they don't want to do?
Well, I'm sure some humans probably do want to do that.
Okay. So, how do you account for that in your thinking?
Yeah. It's a good question. Yeah, this problem comes up, I think, in science in general, which is like we kind of like chase knowledge production for the sake of chasing knowledge production, and we don't ask, is this a positive outcome or a negative outcome? And that's why the atomic bomb exists and so on, but yeah, I think it's hard to say because, I mean, ideally, like, I think the best case scenario is that we've since like hundreds of years ago, we can now automate, or not automate, but like, we don't have to do as much as we had to do like 1,000 years ago, right? Because everything's been so advanced, you can buy your food from the grocery store, you can, you know, your water is delivered through magic pipes and it appears or whatever. If in the limit of this, we want an abundant society where, you know, no one has to struggle for getting their next meal, getting their next whatever, because the means of production are taking care of themselves, and then UBI or something like that is distributing wealth to everybody. That's an idealistic outcome. Maybe maybe the mega corporations of the world are going to control everything, and then we're going to be begging on the side of the road for some spare change. Hopefully not, you know, Cyberpunk 2077 or something. So I guess that's the goal of regulation or policymakers and so on. But I think researchers are primarily driven by what this is really cool. I want to make it do cool stuff. You just cover your eyes.
Gotcha. Okay,
Yeah.
thanks.
Yeah.
We do have a question, I think a follow-up to that on
Yeah.
Zoom, asking, do you think concerns over ethics of robotics is premature given their current limitations?
Yeah, that's a good question. So I think there have always been concerns over automation, right? The Luddites in the 1600s and so on. There's always like, basically people fear change for good reason. The question is automation this time different? Is the rise of machines this time going to be fundamentally different than in every past scenario? You create more jobs. Like you think you're taking away jobs, but then you create a whole new capabilities. Like with the computer, now a lot of jobs rely on the computer, right? Kind of yes and no in that, like, these systems today are still very limited. Like they having worked with a robot, once you've worked with a robot, you'll be like, this thing is useless. Like it cannot do anything. Like it's like struggling to. There's a lot of like robot fail compilations you can watch, or it'll just like, you know, like fall over or something. And but they have come a long way, and you know, the big question is whether this current paradigm of like supervised learning at scale is going to do for robotics what it did for language and vision. And a lot of people are pouring a lot of money into this bet, thinking the foundation model for robotics is going to work. In fact, like almost everybody is trying to do this, but no one has shown that it works yet because data has been a bottleneck, because we don't know the scaling laws for these kinds of things. You know, it could take an insane amount of data to even be that level of proficient. It kind of works for self-driving cars, so that's somewhat of a proof of concept. So I would say there's no reason to sound the alarm yet, but ask me again in 10 years, 5-10 years. Yeah.
All right, let's do Ryan around. All right, well, medicine sets up our final slide. I just want to say thank you to Ibles and Ryan for the fantastic, very engaging talks that we had tonight. And also thank you very much for our audience, both in person and online, to join us tonight. And if you really enjoy these talks and are not currently set up to hear about future talks, you can join us. Join our mailing list with this QR code. Yes, thank you, fantastic. We have our seminars every third Tuesday of the month. So our next seminar will be on April 16th, 5:30, same spot. And we also upload these seminar videos to our YouTube page where you can find our archives. And also we'll send out a post-seminar email with resources that we gather from our speakers on these topics. So if you join the email list now, you'll get the email. Yeah, thank you so much for joining us tonight. And until next time, I hope everyone has a great month.
Thank you so much. These were great talks.